have reached the most delicate moment, matrix multiplication. It's not difficult, it's very mechanical, and you'll see that you'll master it in the next few minutes. But like all new things, it requires some time. I urge you to pause the video and reflect on each of the aspects I'm going to explain. Let's get to it.
Binnacle project.
Let's proceed to multiply these two matrices. The first thing you'll notice is that they have different dimensions. Indeed, the first is a 2x3 matrix, while the second is a 3x4 matrix. How can we perform the operation? The first thing you need to do is a dimensional check. As you can see, I want you to write down the dimensions under each matrix. Well, if the inner subscripts, which I'm showing you, are the same, it means the product can be performed. If they were different, this operation could not be performed. Capiche? The second thing, the outer subscripts, in this case, the 2 and the 4, tell us the dimension of the result. Here, we will end up with a 2x4 matrix, and my advice is that you prepare a 2x4 template like the one you are seeing to ensure you finish the operation correctly. Next, I need a finger from your left hand to traverse the left matrix, a finger from your right hand to traverse the right matrix, and a scratch paper or a calculator to obtain the final result, though it's better to do it in your head. Now, are you ready? We proceed to calculate the 1-1 position. To do this, we take row 1 from the first matrix and multiply it by column 1 from the second matrix. Stretch out your fingers and do it with me. 2 times 1 is 2. -1 times -3 is 3. 4 times 0 is 0. The result is 5. Pause the video and look again at what I've done, because it's what we will have to do until we finish the operation. Let's continue. We proceed to calculate the position 1, 2, that is row 1, column 2. Use your left hand to traverse row 1 and your right hand to move down column 2. And we do 2 times -2 is -4. -1 times 4 is -4. And 4 times 3 is 12. The result is 4. Are you getting the hang of it? Stick with me to the end, and then we can do a matrix multiplication separately. Let's continue. We calculate position 1, 3, that is row 1, column 3. Use your left hand to traverse row 1 and your right hand to move down column 3. And we do 2 times 3 is 6. -1 times 1 is -1. And 4 times -1 is -4. The result is 1. Let's continue. We calculate position 1, 4, that is row 1, column 4. Use your left hand to traverse row 1 and your right hand to move down column 4. And we do 2 times 1 is 2. -1 times -2 is 2. And 4 times 3 is 12. The result is 16. Let's continue. We calculate position 2, 1, that is row 2, column 1. Use your left hand to traverse row 2 of the first matrix and your right hand to move down column 1 of the second matrix. And we do 1 times 1 is 1. 3 times -3 is -9. And -2 times 0 is 0. The result is -8. Let's continue. We calculate position 2, 2, that is row 2, column 2. Use your left hand to traverse row 2 and your right hand to move down column 2. And we do 1 times -2 is -2. 3 times 4 is 12. And -2 times 3 is -6. The result is 4. Let's continue. Not much left now. We calculate position 2, 3, that is row 2, column 3. Use your left hand to traverse row 2 of the first matrix and your right hand to move down column 3 of the second matrix. And we do 1 times 3 is 3. 3 times 1 is 3. And -2 times -1 is 2. The result is 8. Let's continue. Finally, we calculate position to 4, that is, row 2, column 4. Use your left hand to traverse row 2 of the first matrix and your right hand to move down column 4 of the second matrix. And we do 1 times 1 is 1, 3 times -2 is -6, and -2 times 3 is -6. The result is -11. What do you think? I know that the first time you see a matrix multiplication, it might seem confusing. That's normal. It seemed that way to me too. But once you get the hang of it, it's very easy. Pause the video and do it on your note sheet. Rewind video as many times as you need until you get the correct result. Don't forget what we've done. First, dimensional check to see if the operation can be done, and to know the dimension of the result. Second, look at the element we are going to calculate to know which row from the first matrix and which column from the second matrix we need to traverse with our fingers. Keep at it. You'll do it even better than me. Shall we do a second example, but this time separating our knowledge? I'll do it on my own and you do yours, and let's see if we get the same result. If you want, I can join you in this dimensional check, and then we can do the operation separately. Look. Let's multiply these two matrices. The first is a 3x2 matrix, and the second is a 2x2 matrix. As you can see, the inner subscripts, being equal, indicate that the operation can be performed. On the other hand, the outer subscripts inform us that the result will be a 3x2 matrix. We set up a 3x2 template, and now I lower my voice and I will gradually provide the result for each position. You do it too in silence, and let's see if we get the same result. Let's go for it. Did you get the matrix? I'll pass it by rows. 9 1, 8 4, 2 0? I hope so! If not, rewind the video a few minutes to the start of the operation, slow down the speed, and observe each step because, as you can see, I am performing the operation for you. Now, let's continue.
Binnacle Project.
Now that you know how to multiply matrices, I need to tell you some very important details you must know. The first is as follows. From a young age, we grew up with the commutative property of multiplication, that is, 5 times 4 is the same as 4 times 5. I'm afraid that ends here. If we think about the previous example, we were able to multiply matrix A, dimension 3 by 2, by matrix B, dimension 2 by 2. Could we do it the other way around? Let's see. If we now attempt to multiply matrix B, dimension 2 by 2, by matrix A, 3 by 2, we see that the inner subscripts no longer match, which tells us that the operation cannot be performed. A multiplied by B was possible, but B multiplied by A is not. As you can see, the old commutative property does not exist here. To consolidate this idea, let's do the following example together. Let's multiply these two matrices, C and E. First, C by D, and second, D by C, and you'll see that we will have radically different results. Let's start. If we do C multiplied by D, when performing the dimensional check, we see that it is possible. And what will the dimension of the result be? As you can see, it will result in a 1 by 1 matrix. Left hand on row 1 and right hand on column 1. 2 times 4 is 8. -3 times -2 is 6. And 1 times 5 is 5. The result is 19. Now, let's do it the other way around, d multiplied by c. This time, we see that fortunately, we can do it, as indicated by the inner subscripts. But we can already see that the result will be a 3 by 3 matrix, which is radically different from the previous result. Let's finish the example and continue practicing. Let's calculate position 1, 1. Left hand to traverse row 1 and right hand to move down column 1. The result is 8. Position 1, 2. Left hand to traverse row 1 and right hand to move down column 2. The result is -12. Position 1, 3. Left hand to traverse row 1 and right hand to move down column 3. The result is 4. Position 2, 1. Left hand to traverse row 2 and right hand to move down column 1. The result is -4. Position 2, 2. Left hand to traverse row 2 and right hand to move down column 2. The result is 6. Position 2, 3. Left hand to traverse row 2 and right hand to move down column 3. The result is -2. Position 3, 1. Left hand to traverse row 3 and right hand to move down column 1. The result is 10. Position 3, 2. Left hand to traverse row 3 and right hand to move down column 2. The result is -15. And finally, position 3, 3. Left hand to traverse row 3 and right hand to move down column 3. The result is 5. As you can see, doing c multiplied by d is nothing like doing d multiplied by c. If by chance or by design, two matrices A and B yield the same result when doing A multiplied by B as when doing B multiplied by A, they are said to be commutative matrices. For this to be possible, they must have been designed with this idea in mind, but in general, matrix multiplication is not commutative, as you have just seen. Here I show you two matrices A and B that are commutative. They give the same result whether you do A multiplied by B or B multiplied by A. Pause the video if you want to check this, which I strongly recommend, and you'll see that they yield the same result. But this is purely coincidental or the result of intentional design. In general, in matrix multiplication, the all commutative property does not exist.
Binnacle Project.
As I mentioned in the previous video, when I introduced the identity matrix, I told you it would act like the traditional number 1. So here it is. Let's multiply the following matrix, let's call it E, dimension 2 by 3, by the identity matrix. Logically, we must choose the dimension of the identity matrix appropriately, which must be of order 3 for this product to be possible. The result, as you can see, will be another 2 by 3 matrix. And if you do it carefully, I recommend that you pause the video and do it slowly in your notebook, or slow down the speed so that you can see the details of the explanation you're watching. Look who appears! The same matrix E. Just as I promised, the identity matrix acts like the traditional number 1, because when you multiply a number by 1, it yields the same number. But there is more. What if we place the identity matrix on the left side? We've grown up knowing that 1 times any number is also equal to that same number. You'll see that we come to the same conclusion. Only now we must place the identity matrix of order 2 for this operation to be possible. If you do it carefully, and as you can see in this explanation, the result of multiplying the identity matrix by any matrix is the same matrix. As I have been telling you for a while, I invite you, I implore you, I demand you to pause the video or rewind and reduce the speed so that you can verify for yourself that this is true.
Binnacle Project.
Without meaning to bore you, I once again need to inform you about the properties of matrix multiplication so that you always stand on solid ground. You will see that with what you have learned, the following properties are very intuitive and even obvious. The first is the associative property of multiplication. Multiplying A and B first, and then the result with C, yields the same as first multiplying B and C, and then the result with A. The second is the existence of the multiplicative identity element, or for friends, the identity matrix. Multiplying I by A is the same as multiplying A by I, and this will give us matrix A, just like the number 1 we've always known. It's that simple. The third is the right distributed property, i.e. A plus B multiplied by C is the same as A multiplied by C added to B multiplied by C. And the left distributive property, i.e. multiplying C by the result of A plus B, is the same as multiplying C and A and adding the result of C multiplied by B. It might sound complicated, but as you can see in the animations, it is quite intuitive. The fourth and last is the closure property. The product of matrices will always give us another matrix, that is, a mathematical object that belongs to the world of its parents, which are also matrices. Again, and in case someone asks you in a nightclub someday, the fact that this operation, product, applied to these mathematical objects, the matrices, fulfills these four properties, means that we are dealing with a not necessarily commutative ring. And that's it. This video was tougher, wasn't it? Don't despair, because I'm here to help you. This time you've learned how to multiply matrices and gained very important insights about this new operation. Replay the parts where you felt lost, slow down where you need it, make mistakes, start over. That's how you learned this art called mathematics, which, make no mistake, will take you to places you never imagined. I'll see you on the next journey. See you soon!